Mm-hmm.
Okay, now I'm going to share my screen. Should share my screen, right?
Mm-hmm.
Share PowerPoint, but all right, so let me get the PowerPoint open. Actually, I think I'll just share the PowerPoint. You see, oh, now here's the problem. Okay, I need to swap displays. Okay, that worked, except that I need the notes.
Mm-hmm.
So I need to go back.
Do you have so you're set up to mirror displays rather than extend displays?
Let's see.
It's not going to be under here. It's probably going to be under your settings in your computer.
Okay.
So go to your
Yep.
I think I'm going to go to Apple thing right there. Yeah, and the display, and you should be able to say extend display rather than mirror display.
It says mirror, so I
Yep.
want
Say extend. Oh, or maybe just say stop mirror. It does it.
to. Yeah. Okay.
And so now you'll have to drag things over to the other window.
Okay. So now I want to.
It does that. So now when you say share, you should be able to select the
I'm still sharing.
say stop share,
Okay.
and then say share again here. You should be able to select the window with the presentation on it. Perfect. There you go.
All right.
Now I see it.
Perfect. I'm gonna hide this.
You don't need to do anything to that. Don't click that because that'll end the Zoom. You're sharing already.
Yeah, I'll just close it.
Yeah, you can minimize it for sure. Yep. You're good.
Okay.
Great.
Whoa. We're crushing this.
Yeah, good. All right. Well, thanks everyone for your patience. That. So that sciences, and laboratory. She was a PhD in biological sciences at Columbia University in 1989, and her current research focuses on the geophysical evolution of small solar system bodies and ice humans. She led the NASA Dawn mission as a deputy principal investigator in vital sciences. So my role in the mission phase for that mission. Currently, she is a co-investigator on NASA's exciting mission and leads the investigation as a principal. She's a fellow of the Geological Society of America and member of the International Academy of Astronautics, and astronaut 10,724 is named Carol Raymond and was named to acknowledge Dr. Raymond's contributions to planetary science with the Dawn mission. So with that, let's welcome Dr. Carol Raymond.
Thank you, Brian. Really happy to be here today to share the good news about this mission. Europa Clipper is encapsulated in the fairing at the top of a SpaceX Falcon 9 rocket. It would have been launching tomorrow if not for Hurricane Milton. It is tucked safely into the hangar at the launch pad, which is rated for a Category 5 storm, where it's going to ride out the hurricane. And then when it's safe, they're going to roll it out, stand it up on the launch pad and get it off, probably this weekend. So keep tabs on the hurricane and look for the launch coming up soon. So tonight, I'm going to give you an overview of this fascinating moon, Europa. It's a moon of Jupiter. And it's about the same size as our Earth's moon, but it's a very different beast. And we think it's one of the most exciting places to visit in the solar system. And I'm going to tell you why. If I can get this to move. So Europa is one of the 4 large Galilean satellites. Satellites are objects that orbit around a planet. Callisto is the farthest from Jupiter. It's very old. As you can see, it's covered with craters. That's all the bright spots on it. And that indicates a very old surface. You can think about craters as like bugs on your windshield, right? You're driving along and if you have the same number of bugs in the air, the farther you go, the longer the time, the more bugs you get on the windshield. It's kind of like that with craters. There's impact flux. The impactors are constantly coming down. And if nothing wipes those spots off the surface, which is a process we call resurfacing, then they remain. And so you can kind of date a surface by the number of craters. The next moon in towards Jupiter is Ganymede, also very large. And it has less craters and some tectonic features. And I know you all know about tectonics because you live close to Yellowstone. The Snake River is a rift. Snake River Valley is a rift. We have, faults all through the Western US. Well, Ganymede has evidence of some tectonics as well. So Europa, now the next one in towards Jupiter looks quite different. It has almost no craters, and it's got a very young surface. Has a lot of cracks and disrupted areas. And we're going to look at those in some detail. The next one in, Io, that beautiful yellow pockmarked surface, is the most volcanically active body in the solar system. And these 4 are called the Galilean satellites because they're first discovered by Galileo in the 1600s. And they're the first objects in the solar system discovered to be orbiting around another body. So in the last few hundred years, they've gone from these points of light, and that's Galileo's sketch of what he was seeing up there, to being worlds in and of themselves. And they were all visited in the 1990s by the Galileo spacecraft, aptly named, another NASA mission. So while Europa is about the same size as Earth's moon, the images reveal a world that looks very different. The surface is covered not with craters, but with long linear features, cracks, ridges, and they can go for thousands of kilometers across the surface. And in this really interesting close-up, you can see that these cracks have kind of a narrow depression, and then they have some ridges on either side, and they cross-cut each other. And anytime you see one sitting on top of another, that means the one on top is younger. So we can see this is a good illustration of what we call superposition in geology, where you just look at how things are relative to each other and you can tell their relative ages. So we know that something's been going on over time that's modified the surface of Europa. There's also these areas that are disrupted called chaos terrain, and they look kind of like icebergs. These pieces where the crust has been broken up and some pieces are rotated, tilted, and then they freeze into a new position. So that kind of process says that there's something active going on under the surface. So I said there was only a few impact craters on the surface. And this is one of the most recent ones. It's called Quill. And you can tell it's young because number one, you can see it and they get erased over time, but also it has this beautiful system of bright rays surrounding this central dark circle. There's also these strange dark features called lenticulae, which just means kind of a bean-shaped, not a name for a lentil, but it's kind of like that, little bean-shaped features on the surface, sometimes called pits or spots or domes, depending on their morphology. And they could be locations where subsurface material is coming up and reaching the surface or interacting with that surface layer. So all of this says there's a lot of things going on where the subsurface of Europa and the surface are in communication. And if we look at the big picture, all of those features that tell us there's activity, plus other evidence we're going to talk about a little bit, leads us to believe there's a large global subsurface ocean on Europa. Back in the Galileo era, magnetic field measurements showed that there was a conducting layer under the surface because the magnetic field of Jupiter changes its direction on a regular basis, because while Europa is going around Jupiter in its essentially equatorial plane, Jupiter's magnetic field axis is tilted, the same as Earth's axis is tilted. And so its magnetic field equator is at an angle to the ecliptic plane where the satellites are orbiting. And so as Europa views Jupiter rotating, so it's their relative reference frame, it's seeing this magnetic field that's changing up and down, positive and negative, on an 11-hour period. And that induces a response current in this salty conductive layer, tries to cancel out that field. And that's what we measure. So that's called the induction signal. And that's how the subsurface conducting layer was directly sensed, was this magnetic signature. Also, the gravity field told us that there was something less dense between the surface and the center, and also the presence of a metallic core or a density concentration in the center. So we learned a lot from Galileo about the layering of the interior, and because of all that, the chaos and the lenticulae and the lineations on the surface, we knew there was a lot of geologic activity going on. So we believe that the subsurface ocean on Europa has more water than all of the Earth's oceans combined. And it's a body about the size of Earth's moon. And then on Earth, where we find water, we find life. And while we are putting a lot of resources into looking for life on Mars, and that's part of what the purpose of the Mars sample return mission is, life on Mars is likely fossilized life, or what we can access from the surface is likely, past life, where there might be a deep biosphere on Mars, where there's warm water circulating in the rocks, but right now there's no surface water. There's very little surface ice, so it's probably not harboring extant life or life in the present. But in the case of Europa, with this giant ocean of liquid water, it begs the question of whether it could have or is supporting life. So then you might ask the question, well, this body is way out there in the solar system, 5 AU, so it's 5 times the distance that the Earth is from the sun. There's very little heat, very little solar insulation reaching it. So why is it warm in the center? And the answer is tidal heating. We're gonna have to go back and make that start again. Okay, so as both of these going? Okay. So as Europa is going around Jupiter, you see it's like closer and then it's farther away. And when it's close, it's being pulled into this more bulgy shape. And then as it gets farther away, that relaxes a bit. And this happens, over its orbital period. So it's flexing back and forth and back and forth. It creates friction in the interior, and then friction equals heat. So it heats the interior and it keeps it warm enough that liquid water is stable. The surface is covered with ice, and one of the goals of the mission is to measure how thick that ice is. But we know that that ocean, there's warmth in the subsurface, and it's creating this subsurface ocean. So it's thought that tidal heating is really concentrated in this boundary layer between the ice and the ocean. And some of the heat, if the ice is fairly warm, then it can be moving, it can be flowing. And that can lead to some interesting features where the ice and the ice is cracking up, like you're seeing in this cartoon here, where the warmer ice can deform the colder, stiffer ice, and that can cause these disruptive surface features. And eventually, we think could create pathways where the ocean can get to the surface, so-called plumes, and these plumes will vent material from the ocean onto the surface. So the mission is going to be on the lookout for plumes. So this is another high resolution set of images that was taken by Galileo of an area called Connemara Chaos. And it's showing the details of the disrupted surface. And it's just a lot of really interesting features. And honestly, there's a lot of hypotheses, but we don't really know how they formed. This is an artist's rendition of one of the models that says, maybe a lens of liquid water forms in the ice shell, and that creates cracks going to the surface, basically a zone of weakness. And then those pieces at the surface are kind of floating around like icebergs for a while. And then eventually this area will freeze back and you're left with this disrupted surface. So this is another artist's rendition of what the interior of Europa might be like, with that ice shell, with this cold, brittle surface, with all these tectonic features, with this warmer, possibly convecting ice and conduits in communication with the subsurface ocean. And then we also pose a question, could there be hydrothermal systems on the seafloor of Europa, which are bringing material from the mantle, the rocks, into that ocean? And this is evidence that there could be ingredients for life, because we have water more than all of Earth's oceans, and then we have essential elements. That's the carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfate that came from the original material, and also come from impactors that are hitting the surface. There's chemical energy coming from above and below. We have radiation hitting the surface, and that's driving some chemical processes. We have rock-water interactions going on at the seafloor, and that's creating chemical energy. So there's water, the essential elements, and energy, and then the whole system's been basically simmering for 4 billion years, which provides opportunities for very simple prebiotic molecules to form, and then perhaps they have reached the stage where where life has taken hold. So this is pretty exciting. And here is a wonderful video of what hydrothermal vents on our seafloor look like. There's an abundance of life in a place where sunlight doesn't reach. It's driven by the chemical energy that is from this interaction of the water with the rock at high temperature. The water is percolating down through cracks in the seafloor. It's being heated because we're at mid-ocean ridge where magma is rising from the mantle. And so that water is being heated, interacts with the rock, it changes the chemistry, releases a lot of new elements into the system, and it's feeding these complex systems at these hydrothermal vents. So now we'll talk a little bit more detail about what Europa Clipper is going to do. It has three main sets of objectives that deal with the ice shell in the ocean, the composition of the surface geology, and then these inform us of current activity, that, whether something's going on today. Are there plumes? Are there, cracks and features forming? And then also the data will be used to develop a reconnaissance data set in case we want to go back with a lander and actually land on the surface and interrogate this material more closely. The instruments, this mission carries 9 instruments and then uses the communication system to measure the gravitational, the gravity of the body. So one set of instruments is so-called remote sensing, which means it's looking from a distance and taking measurements. We have ultraviolet spectrograph, which characterizes the surface, any plumes, atmosphere, and the atmospheric composition. We have narrow and wide angle cameras, and you're going to see a lot of pictures. So that camera is going to be your eyes on Europa. And these are mapping this alien landscape in 3D, providing color to help us with understanding the composition. And then it's helped in that with our IR spectrometer, which is looking at the surface in wavelengths that our eyes can't see, but show us what minerals are are on the surface. And that gives us an idea of what the makeup of that rock is. Or in this case, it's ice with material sitting on top. We have a thermal imager, which is basically just looking for hotspots. If there are plumes coming from the ocean, they're thermally driven. And we expect we'll see that thermal signal at the place where the plume is coming out. And this is how, this is also seen on Europa, on Enceladus, the moon of Saturn, which has been ejecting material into space from a feature called the tiger stripes, also due to tidal flexing. And it's kind of like geysers at Yellowstone. We can predict when they're going to happen, and they happen periodically. So Europa, we don't have that kind of certainty about where plumes might be or what's driving them or their frequency or cyclicity. So we're looking for all of that information. Then we have an ice penetrating radar, and this is essentially looking through that ice shell, and finding all the, looking at the plumbing system, basically. Are there pipes coming from the ocean? Are there little puddles in the middle of the ice, so-called lenses? And what are the thermal physical properties? How warm is it? Is it convecting? Things like that. Okay, then we have a suite that we call in situ. And that means we're sensing something about the body itself, but it's an inherent property, not something you view, or we're looking at the atmosphere. And so the mass spectrometer can look at the individual elements, molecules of the atmosphere. The dust analyzer is also giving us composition of the little pieces of dust that are coming off of the surface. The magnetometer is sensing the ocean properties. I talked about the induced field before, so we're going to do this with more accuracy so that we can not only detect that an ocean is there, but we can say something about its thickness, like how deep is it, how thick is it, and what's its salinity. Or we measure the conductivity, and the conductivity can be turned into salinity when we have information about the composition of the surface. And then this PIMS instrument is looking at the plasma, and we need that information because we're interested in the plasma environment, but also plasma carries the magnetic field. And so it can create a nuisance signal for sensing the ocean. And we want to be able to confidently separate those two things out. And then finally, I talked about the gravity and radio science, which we use high gain, and we use any antenna that's communicating with the Earth, and we just measure the Doppler shift of this radio wave. And that tells us that the spacecraft is being pulled a little bit towards Europa, or it's moving in and out relative to Europa as a function of the force of gravity. So it's just amazing that from Earth, we can track a spacecraft at 5 AU, measure these little perturbations accurately enough to get the gravity of that body. But it's true. Okay, so where are these on the spacecraft? This is the spacecraft all festooned with all its instruments. You notice it's got these very large solar arrays. It has the high gain antenna is that thing sitting on top. The magnetometer boom, which carries 3 sensors, is 8.5 meters long. Then we have a deck of instruments that are looking down. And that's the cameras and the spectrometers that want to look at the surface. So as we fly over Europa, that deck is going to be pointed at the surface and tracking it. And then we've got forward pointed instruments that are more interested in looking at the atmosphere, scanning for plumes, looking for the dust that's being lofted off and sniffing it and tasting it. And then the radar. The radar is these long antennas that are attached to the solar array, and that we have the high frequency at 9 megahertz and very high frequency at 60 megahertz. And so that radar, as I said, is going to be probing the ice shell. Okay, so again, here's a nice CAD of the spacecraft, and you can see some of the features as it's rotating around there. The camera, the imaging system, and the mapping spectrometer, and the ETHEMIS, the thermal imager, are all looking at the surface. And then the dust analyzer and the mass spectrometer and the UBS are mainly looking forward to the atmosphere. And then I talked about the antennas, and then the PIMS cups are on both sides of the instrument to gather the plasma. Basically, it doesn't have a way to suck it in, so it's just the direction that the spacecraft is pointed in. The plasma will enter the cup and it will be measured. And then the boom, as I mentioned. Okay, so this is a nice animation that if you follow that green arrow, that's showing you the direction of the magnetic field sensed at Europa. And you can see that it's kind of swinging back and forth as Europa goes around. It goes around Jupiter. First, it's watching Jupiter spin, and then it's going around Jupiter. So this environment, Jupiter's magnetic field is really intense. It's very large. And that means that any material that's enters the region that Jupiter is influencing becomes charged. So that neutral species become ionized, and then the ions get accelerated in the magnetic field. And I said that Io was the most volcanically active moon in the solar system, body in the solar system. It's spewing a lot of material out. And that is creating this torus, which is just a big donut around Jupiter. And that torus is highly charged material. And so it carries the magnetic field with it. A lot of radiation. So Europa, being right next to Io, is basically in the torus. It's being bathed in this radiation. And so if you send a spacecraft to Europa, an orbiter, to stay close to it, it would take a lot of shielding, lead, to make it last a few months to a year. So you got to do something more clever. And this is what this is the solution that Europa Clipper team came up with. a global web of flybys. So instead of orbiting around continuously, the spacecraft flies by Europa and then goes way out, away from that high radiation environment, and then comes back in. So it gets nearly 50 of these flybys over 3.5 years, and can survive the high radiation environment using, and also using this kind of simple, repetitive operations. So this is kind of a fun animation where you see the spacecraft just came in, it's being captured by Jupiter now. You have a radiation dosimeter up there that's showing you the instantaneous radiation you're getting on each of these flybys. So remember I said when it gets close in to Jupiter, you get a lot of radiation, then it comes back out. And then at the bottom, it's showing the total dose. So this is a really nice, colorful figure showing how the orbit evolves over time. And the way they move these petals, these so-called petals, the bunches of flybys that are all kind of in the same direction or the same geometry, is by flying by one of those other big moons like Callisto or Ganymede. It's like a little, gives it a little torque, kicks it into another type of orbit around Europa. So at the end, we've gotten a really nice data set of Europa for a total dose, which can be survived by the spacecraft. All right. We have some pictures of the instruments. You'll just notice that people wear bunny suits and gloves, and everybody works in a clean room, and everything is done with a lot of care. This is the magnetometer boom before it was wrapped up. It's a very gossamer kind of structure, 8.5 meters long. The imaging instruments and the thermal imager, and then over there at the end, the reason antennas are being tested at an antenna range at JPL. So this is also just a very involved process of building, testing, and making sure everything's going to work, because you can't fix it once it's gone. And here it is being integrated onto the main body of the spacecraft. So you see some of the instruments there. This big plate over at the side is the nadir deck. And you see those two cylinders, and I think those are the star trackers. And here's the solar array, so you get an idea of how big that is. This is the whole spacecraft having been completely integrated and wrapped up. And now it's entering a chamber. So you can kind of see, you don't see the top of the chamber, but you see spacecraft's kind of hanging there on these chains, these cables. And then they close up the chamber, they pump it down to vacuum because there's space is a vacuum. And then they run through the whole temperature profile of the whole mission. So, and test their thermal models and make sure they really understand how the spacecraft's going to react to those temperatures. Okay, and this is just a kind of fun comparison of the size. This is the rocket that takes Artemis, will take the astronauts to the moon, Statue of Liberty, 6 stacked school buses. We always have to have school buses in NASA materials. I don't know why, because almost nobody takes a school bus anymore. SpaceX Falcon Heavy, that's the rocket that is going to launch us off the Earth. And then here's the size of our spacecraft, and it's about the size of a basketball court. Our trajectory launches this week. Then we go by Mars in February, and we get a gravity assist. So that's just like, a slingshot, basically. When we feel Mars's tug, it pushes us away and gives us a little boost. Then we come back around and we do the same thing with the Earth. And then we're off to Jupiter. And we get to Jupiter, we enter orbit in April of 2030. So this takes a while. And again, here's a little animation of the trajectory, and I'm going to skip this because I think the next one is more interesting. Okay, and this is a video of the spacecraft. Well, it's an animation of the spacecraft showing, the full flight system flying past Europa. So here is a good time to say, you notice that it's all wrapped up. And we have to put blankets all over it to protect it from the little pieces of dust, the micrometeoroids that'll bombard it as it goes through space, and also for thermal management. And those blankets are actually patterned and sewn by hand. So this is, the spacecraft is built by hand by a lot of people, and they're very good at what they do. Very meticulous, very dedicated. And it's the only way you can make a machine like this work in this harsh environment and last as long as it does. And I don't know how many of you know about the Voyager spacecraft, but Voyager 1 and 2, just passed their 40th anniversary, and Voyager 2 is still sending data back from outside of our solar system. Okay, so I said here's another animation of the tour, but it's sped up a little bit. So you see up there, it says April of 2032. It takes a while to phase in the orbit so that we start going past Europa. We have to fly by Callisto and Ganymede and do all this dancing around with those are gravity assists as well. And then you finally start doing the flybys of Europa. And then I think, yeah, so this one will go super fast and start showing you from orbit insertion, which that was the first orbit. And then, as I said, we're phasing it in with moon flybys. And now we're into the tour, and we're doing the repetitive flybys and we're catching like one side of Europa. And most of the flybys are on the subjovian, means the face of Europa that faces Jupiter, because it's in a lock with Jupiter as it goes around. It's called a resonance. And then it switches, so we look at the other side, the anti-Jovian. It's hard to look at the leading and trailing. So leading is the direction of motion and trailing is behind in the wake, because of the way the spacecraft is orbiting really Jupiter, and we're just sending it by Europa. So we can't really get the other direction easily. So so now you can see how it's moving around, and now it's done. And here is just another view of that to show the complexity. I'll just make a point to say, the guys who do this, the guys and women that do this are, mostly they're mathematicians, and they're really good at what they do. And coming up with this kind of a tour is just mind-boggling. The tools and they have to run these models on supercomputers for hours and hours and hours. And they listen to us, the scientists. What do you want? What are you looking for? Say, we want to see that feature. And each investigation has their own little requirement set, and they take it all in as constraints to build a tour that can do all that, and and not bust the radiation budget. Okay, so now I'm going to do a little bit of the cool stuff that's on the spacecraft. I mentioned Voyager. You may remember the Voyager record. It was actually like an LP that was that was engraved with a lot of messages. Well, we have a message in the bottle, and that it was a message in the bottle campaign. Send your name to Europa, and 2.6 million people participated. Their names were engraved on the spacecraft and in its ship, and they're going. And then we have a vault plate, and it's a tantalum metal plate, and it seals the opening to the vault and includes a poem and other designs. So now I'm going to play this poem animation. So before I start it, the poem was written by Ada Limon, who's the US Poet Laureate. And she was asked to do this. She was quite intimidated to write a poem for a spacecraft going to Europa, and she knocked it out of the park. So she's going to read her poem to you.
A poem for Europa. Arching under the night sky, inky with black expansiveness, We point to the planets we know. We pin quick wishes on stars. From Earth, we read the sky as if it is an unerring book of the universe, expert and evident. Still, there are mysteries below our sky. The whale song, the songbird singing its call in the bough of a wind-shaken tree. We are creatures of constant awe, curious at beauty, at leaf and blossom, at grief and pleasure, sun and shadow. And it is not darkness that unites us, not the cold distance of space, but the offering of water. Each drop of rain, each rivulet, each pulse, each vein. Oh, second moon, we too are made of water, of vast and beckoning seas. We too are made of wonders, of great and ordinary loves, of small invisible worlds, of a need to call out through the dark.
Still get chills every time I hear that. You know, and I think it's a great,
In pray.
it's a great way to demonstrate or to try to convey like what scientists, people like myself and the others who work on this mission are really after. It's not all like facts and figures and, you know, this data or that data. It's really about fundamental things like where did we come from? Is there life out there? And I really feel like she captured that pretty nicely. So that poem is written on the vault plate. It's a picture of Ron Greeley, who was an early promoter of a mission to Europa. So he was a geologist at the University of Arizona. And then this other beautiful Rayburst diagram, those are recordings of the word water in, I think it's 104 languages across the globe, shown as waveforms. So if anyone finds it, they'll have something to think about. And then this is just, you know, saying that we have a lot of materials on the website. If you are a teacher or you know somebody who is, you might want to let them know that they can go download a lot of materials there. And there's a QR code. Anybody? So encourage you to get involved, follow the journey, which I think is going to start this weekend. And I really appreciate you coming and your attention. Thank you very much. How long is it going to last? Yeah, so it will take mid-2030, we're going to run it. And then the primary tour is going to take, well, first we have to get into orbit around Europa, and then the primary tour is about 3.5 years. So all told, 2030 is, you know, it's on the order of 2034. And then if the spacecraft is still healthy, then we will plan to do more. And likely, you know, one of the exciting things is if we do find plumes coming out, then the tour is kind of fixed because there's all these resources that have to be expended in a certain way, you know, so you can't just take a right turn without going through a lot of planning and crunching numbers. So we're probably going to be stuck with the tour unless we, you know, find something that's so compelling that we decide to, you know, to replan. But likely what we're going to do, as long as the radiation isn't killing us, is plan those extra activities for the end. And then we have time, we have to think about the data, and then figure out what to do next. Now, I wanted to mention one thing. relates to how long. And that's that right before we were launching, like literally July. Everything's built, starting to, button everything up, talking about talking about transporting to Kennedy. And it's discovered that some parts on the spacecraft were not performing as they were rated for radiation tolerance. And that's not a good thing when you're going to the most radiation harsh environment in the solar system. And what happened was somebody in a commercial arena alerted somebody on the JPL team that they were seeing this in some of the parts that they had. Said, maybe you should look at this. So look at it, they did, and the initial testing was like not good at all. And then they had to figure out how many of these parts are on the spaceship. There were over 1,500 of these parts. Okay, so I wasn't aware of it. So long story short, every part was mapped, and the lot that it came from, how it was being used, like in what circuit, what were the voltages, what was it supposed to do, because they're used for power switching, management. I mean, it was just, they were everywhere. They were in the instruments, they're in the spacecraft. They're transistors, they're very common person. So then they got every part and went through exhaustive testing to see if they were really going to survive this radiation dose, and also to test how they performed over temperature, because the radiation damage is a function of temperature. And if you're very cold, you get a lot more damage than if you're warm. So, yeah, I'm really oversharing. But long story short, they figured out that that every part was going to survive as long as it needed to that radiation dose that the mission was planned to. And the few parts that were vulnerable, it was understood that if you kept them warmer and there was enough power to do that, then you could undo the radiation damage kind of cyclically and keep them going long enough. I have, in my career, 35 years, I've never seen anything like this. And the fact that it was fixed is phenomenal. So it's a big success story, and that's allowed us to launch and get there on time.
That's in the did you also have
Oh, okay.
yeah.
Okay. So, sorry about that. Oh, definitely need the mic.
Let me get you the you guys by crashing into Jupiter.
Yes, and it's called disposal, and the plan is to crash it into Ganymede. Now you're probably like, what did it do? We don't think Ganymede harbors life, so it was either Callisto or Ganymede. The interesting thing is there's a European mission called JUICE, which is already launched and it's headed towards the Jupiter system, and it's going to do a tour of the moons as well. It's a pretty similar spacecraft and mission, but it's going to settle in at Ganymede and it's going to go into orbit because it doesn't have the same issue with the radiation. So it is not clear if it will still be there and still be, taking data, but it would be quite interesting to crash the Clipper spacecraft into Ganymede and watch what, the plume of material that comes off, see what kind of crater it makes. And the reason it has to be disposed of is to make sure it doesn't fail and crash into Europa, because we may want to go back there. Our spacecraft is cleaned, so we don't bring microbes with us. It's also going to be sterilized by that radiation environment. And then we want to dispose of it so that if we do land and we bring life detection instruments, that we will be measuring Europa and not something else. Great question.
Not really loud, that's okay. Can you hear me?
I can.
Yeah, or
I don't know the people on
they can't hear anyway.
Oh, okay, so I'll repeat. Okay, I'll repeat the question. Sorry.
So you said that science stuff with Ganymede has like, why is that? Because Ganymede, is one of the biggest and sorry, I'm for Arizona State University. Ganymede is one of the things with the magnetosphere on its own, and it's also thought that it might also not have
Yeah.
Please don't question Ganymede.
So, yes, that is a very good question. And the reason is that Ganymede has, its ocean is sandwiched between ice. So there's high pressure ice at the bottom of the ocean, which is keeping it separated from the rock. So we don't think that those really rich processes are going on that with the water rock interaction that are pumping, the new elements into the ocean. So that's the reason why Ganymede doesn't have as high a habitability potential as Europa does.
There's about 2 times the level. What is
Yeah, I don't know if it's this echo or something, but it's still.
So how do you determine how much water is on this, on Europa that you're studying? Like, it said up on your slides, it says about 2 times the amount of water as Earth.
Yeah.
So how of it is like a guess versus like scientific, like data?
Yeah, great question. So there's an estimate based on Galileo. The question is, how do we know how much water is there? And that, it's twice the Earth. Is it a guess or is there something behind it? So it's, I would say it's an educated guess. The Galileo data gave us some very large error bounds, but when we combine what the gravity told us, which gives us the thickness of the ice and the ocean with some error bars, and then we look at what the magnetic field data are telling us with assumptions about, is it sodium chloride? Is it magnesium sulfate? All these assumptions go into it. So you can turn the conductivity into a thickness or thickness conductivity product. So what we can say is that there is more water there because even with the error bars, we know that much. But we really want to know much more precisely how much there is, because it tells us about how the body evolved from its initial state and how long was it habitable? And particularly these questions about how what's the exchange between the seafloor, the ocean, the ice shell, and the surface. And I didn't talk much about the radiation at the surface, but it's also creating a lot of new elements, new compounds that if they return into the the ocean, they bring oxidants. So you have a reducing environment at depth, you have an oxidizing environment at the surface. And so mixing those things together is driving the engine that increases your habitability quotient.
Question about kind of a far-reaching idea, and that is, if we are to land on Europa, are there scientists kind of having some fun thinking about a submarine-style rover?
Yes.
So question is anybody thinking about a rover for Europa? And I say right now that's a bridge too far because the lifetime of the Europa lander, which has been studied quite extensively, is measured on the order of months. And so it's going to have an arm, I say it's going to have an arm. The plan was it would have a way to taste some of the material around it, but a rover would probably not be worth the lifetime. Did I get the question?
Okay, what is submarine? He's asking about
Oh,
submarine.
yeah, submarine. Ooh, yes. Lots of people are dreaming about that. That is, and there's a development that's gone on at JPL, and it's mostly in relation to Enceladus, but it's a snake robot called Eels. And it can maneuver through a crevasse, essentially a crack in the ice, go down and find the water and roam around and make all these measurements. But I mean, now we're talking about a whole level of kind of science fiction that, might turn into reality at some point, but it's hard. And it's easier at Enceladus because we don't have the radiation problem. Enceladus is a moon of Saturn, and it doesn't have that intense radiation. So it's likely going to be something like that at Enceladus before you would see it at Europa. And there is a mission that NASA has, that's part of a planetary decadal survey that says we'd like to send a flagship mission to Enceladus to both do more comprehensive mapping from orbit, as well as a lander that brings a live detection suite and can try to determine whether anything it finds that's coming out of these plumes looks like it has any biosignatures. So that's way in the future, but that's more of a plan than a submarine at this point. Yes.
This mission to look for biomarkers like methane or anything like that?
Okay, the question is, with Clipper, we'll be looking for any biomarkers like methane. So there was a lot that was discovered with the same mass spectrometer and dust analyzer that we're flying on this mission. They're just like cousins, about the habitability or the potential for life at Enceladus by measuring the material in the plumes. So if there is material we can say is spewing out of the ocean, and we know it's oceanic material, and then analyzing that and its composition, what molecules are in there, will tell us something, which it will be interpreted, but the mission is not designed to look for life. And so you won't see seeing that like on the front page of the New York Times, because the data will not support anything that definitive.
Thank you. I was looking for which the goals for our first most of the videos, astronomy, first part of the maybe